I'm going to begin with a quick introduction of NOARK, who we are. We're part of a global organization and are a manufacturer of low voltage electrical components. We specialize in motor controls and circuit protection products. The organization was founded in 2012, regional headquarters in Shanghai, Los Angeles, and Prague in the Czech Republic. And like I said, primary business today is low voltage electrical distribution products and industrial control components. Although over the course of this year, we'll be introducing a series of other products expanding beyond into utilities and renewables and products like that. We're part of an organization called CHINT. CHINT is a fairly large global company founded in 1984, operating in over 30 countries, 30,000 employees, revenues of around 16 billion globally in US dollars. This organization is based primarily or originally in the Asia Pacific area, and in those markets has a commanding market share. In North America, not so much until recently. And we're here to spread the word about our excellent products and many years of experience in manufacturing these products. NOARK, under the CHINT umbrella, has very strong research and development capabilities. All of the products that we offer are our own design. They are designed, tested, and certified for global applications in our test lab and engineering center in Shanghai. Our factories are all world-class quality factories, all ISO 9000 certified, and adhering to the most modern total quality and lean manufacturing practices. In North America, we have two distribution centers, our headquarters location in Pomona, California, and a Canadian warehouse in Kitchener, Ontario. We strive to keep the highest moving items in stock at our two warehouses. And even through the depths of the supply chain issues in the pandemic, we never really missed a beat in terms of delivering product. Our factories remained very reliable in their manufacturing time, and we were able to keep our stock levels intact at our warehouses through it all. So we have got a very, very solid supply chain and logistics capability supporting those two warehouses in North America. All right, so the next slides, I'm going to move into, excuse me, a high level view of what is a circuit breaker. Some of this may be a review for some of you, but it sets the stage for a much deeper conversation on power circuit breakers. So first question is, what is a circuit breaker? So a circuit breaker is an electrical device that's designed to protect an electrical circuit from damage caused by an overload or short circuit conditions. Its basic function is to interrupt the current flow after it detects an abnormal condition. And something that people don't necessarily always recognize is that, driven by the codes and standards that are used to certify a breaker, its primary function is to protect the conductors within a power distribution system. So it protects those conductors from overloads caused by loading the circuit with more current than it can stand, or by short circuit events, which are usually much faster and more intense events that happen in a power distribution system. Conductors based on the electrical codes and standards that we adhere to, they're classed as either feeder conductors or branch circuit conductors. And those two terms are important, and we'll talk a little bit more about them later. In a typical electrical power system, breakers are usually organized in that system in a hierarchy from largest to smallest. So if you think about it in a building or in a machine, you typically have a large circuit protection device or breaker at the main incoming, whether that's the service of a building or the main incoming to a machine. And then the breakers, as the power flow goes through the system, the breakers get successively smaller. So this slide is really intended to illustrate where the different breakers that are in the market are applied within those power systems. So on the very left-hand side at the high end or the incoming part of a power system, this is where our low voltage power circuit breakers come in. They're typically rated up to 635 volts. That's the voltage class that's laid out in the standards. And typically they have an ampacity between 600 and 6,300 amps. Low voltage power breakers have a withstand rating based on a 30 cycle short circuit time. And that's important for coordination when we start looking at how breakers protect different parts of the circuit depending on the magnitude of the fault and where it occurs. Power circuit breakers are typically available in either fixed or drawout type. They're stored energy devices, which I'll explain a little bit more in more detail. And almost universally today, they have electronic trips. Low voltage power circuit breakers are the standard that governs their construction is UL 1066 in the US and CSA number 31 in Canada. If I move on the next breaker to the right, it looks very much like a low voltage circuit breaker. And in fact, it is the same construction, but it's a breaker that's been tested to the molded case breaker standards, which is UL 49 and CSA number 5. And the reason for having the same type of breaker with different ratings is because a molded case circuit breaker, or in this case, an insulated case circuit breaker, is intended to provide protection at that next layer of the power distribution system below the power circuit breakers. So the only real difference in the insulated case breakers is they're tested to a three cycle short time withstand rating. And then moving on to molded case breakers, this is the next layer below the insulated case breakers. And this serves as the primary circuit protection devices that are through the majority of the power distribution system. And these range anywhere from 15 to 3,200 amps. 3 cycle short time withstand, they're fixed mount, and instead of being stored energy, they have a manual toggle operation that I'm sure you're all familiar with. And moving on to miniature circuit breakers, this is at the lowest end, and you'll see that the voltages drop now. So miniature circuit breakers are typically 480, 277 or 240 volt rated. 15 through 100 amps, and these are the last circuit protection device in what's called a branch circuit, and they're usually the last circuit protection between the power distribution system and either a machine, an appliance, or something like a lighting system or an electrical outlet. Okay, so moving on, I'm going to run through some examples of different types of applications where breakers are applied, and I'm going to use buildings as an example, but these scenarios can apply to a machine that has a hierarchy of circuit protection requirements inside it. So in a light commercial building, so this is typically a very small warehouse, a small retail facility, strip malls, those kinds of locations. The utility almost universally enters this building with a 480 volt, or in Canada, a 600 volt service. And the service comes into what's called a service entrance main device. So this is a circuit breaker. It could be a fusible switch that is approved for use as the service entrance main. And that's approved based on its design under the standards, but also by the local utility who is connecting to that device. Power is then distributed through a splitter, and then from the splitter, you can take off a number of smaller breakers. So typically, you wouldn't see in this kind of an application a main breaker above 1200 amps. And then the feeders that come off below it are anywhere from 15 to 800 amps typically. And those larger breakers then would feed a panel board under UL 67, which again would have multi-case breakers inside it. And then moving on to the right, then you would get successively down into both lower voltage and lower ampacity breakers, coming right to the very end to the lighting panel, which would typically be feeding both lighting circuits and receptacles and things like that at 120 volts. Okay, so that's kind of the structure of a light commercial building. In larger commercial buildings, what you see here is you have a much larger ampacity service. So the service entrance main can be up to 6,000 amps. And this is where that insulated case circuit breaker can come into play. So in a service entrance switchboard under UL 891, typically it's a molded case breaker as that main device. But if circumstances require a draw out or a larger ampacity breaker, often it's that insulated case breaker that's used as the main device. A switchboard is a single assembly that contains a cross bus and all of the distribution breakers. So this kind of replaces that single main breaker with a splitter trough and individual feeder breakers from it. And again, it feeds successive layers of distribution through to a CDP type panel board, and ultimately through a transformer down to the lighting and appliance panel board that would be giving you that branch circuit protection. And moving on to even larger facilities, the major difference here is scale in both voltage and ampacity. Many utilities will serve a large industrial or institutional facility with a medium voltage feed. In that case, the owner of the building would be required to have a medium voltage to low voltage substation to bring the voltage down to the usable level of 480 volts or 600 volts in Canada. There's another layer of assembled equipment here, and it's a low voltage switchgear. It's under UL 1558, and it almost exclusively uses power circuit breakers approved to a UL 1066. Those breakers are in the ampacity range of 600 to 5,000 amps. And these assemblies can become very complex because in larger facilities, say a data center, for example, not only will you have the utility service feed coming in, but you could also have a UPS and one or more backup generators that are attached to this power distribution system. So that coordination of all those sources and all of the loads is done within this low voltage switchgear assembly. In industrial facilities, that low voltage switchgear could feed motor control centers where you have industrial processes or manufacturing that needs lots of motor loads fed, and ultimately to CDP type panel boards, and through that whole distribution chain again that you see right down to the lighting and appliance panel boards. Okay, so that's kind of the overview of where the different types of breakers are used. So just to recap, for the UL 1066 type breakers, they primarily show up in low voltage switchgear and as the main devices in low voltage switchboards. Okay. So just the next couple of slides here are getting a little bit deeper into the construction of a power circuit breaker. And by the way, these we call it power circuit breakers. Often they're called air circuit breakers. There's a few different names for these devices. But for our purposes today, we'll either call them a power circuit breaker or an air circuit breaker, or an ACB, as it's commonly known. Critical key components in the circuit breaker. If you view this from the front, you'll see that there's a place for accessories, and we'll be going into a lot more detail into what the accessories are. But functionally, inside the breaker, the primary components are the moving and stationary contacts. So these are the contacts that open and close the circuit. They're typically large copper formed contacts that open and close with the mechanism. The mechanism is driven by some very large springs. So you'll see when we get into the next couple of slides, you'll see how they operate. So there's the contacts are operated by the springs. There's a charging handle, which is item number 9, just on the lower left-hand side of this graphic. So the charging handle allows you to charge the springs manually by hand. And then there's also something called a motor operator, which charges those springs based on an electrical signal and a motor that winds the springs up. And lastly, there's something called a trip unit, which is an electronic device that works with the current sensors you see on the right-hand side in green. The trip unit and the current sensors work together to sense the current flowing through the breaker, and it provides all of the tripping functions that we'll talk about in a bit. So the principles of operation for an air circuit breaker, it's called a two-step stored energy mechanism. So it starts with the closing spring, which the springs are very large and very powerful, and that's required because you need a very fast operation in order to close and open the contacts and reduce the arcing that happens. The spring can be charged independently of the position of the breaker. So at any point in the operation of the breaker, the spring can be charged. And there's a separate trip spring. So the way this works is the spring that you see on the left-hand side is charged either manually with the handle or through the motor operator. And that's the closing spring. And when it closes the breaker, it compresses the trip spring. And so what that means is that the trip spring always is compressed when the breaker is closed. And that means the breaker can be opened regardless of what happens with the charging status of the of the closing spring. And then the sequence of operation is what allows the breaker to very quickly close and reclose whenever it's required. So the sequence starts with the breaker closed. The trip spring is charged. The closing spring is charged. So that's sort of the starting point for this sequence. If the breaker opens on a fault and then gets a reclose signal, it will attempt to close again because the springs are available. But then the breaker can open on a fault condition again. And so the springs are always charged in the right sequence to allow that breaker to reliably open on a fault condition. Another important part of the operation of a breaker is the arc quenching capability of the breaker. So if you look at the image on the left-hand side, the breaker's closed, it's operating normally. And then a fault happens and the trip unit senses the current is rising and it signals the breaker to open. And when the breaker opens, as the contacts begin to separate, ionized gases form an arc between the two contacts. And that's typically a bad thing because those arcs are what deliver the heat and explosive energy that comes with a fault. The motion of the contacts and the shape of the contacts begins to push that arc upward toward the arc chutes, which are the lines that you see up at the top. And then as the arc approaches the arc chutes, it generates magnetic forces that draw the arc into the arc chutes, and it breaks the arc up into many smaller arcs. Then they have an opportunity to cool and dissipate. And that's what keeps the breaker from basically blowing up as that arc begins to form, because the contacts force the arc upward into the arc chutes, and the arc chutes split it up and dissipate the energy of that arc. So that's kind of the basic principles of operation. And I'm going to turn it over to Kunmi from this point so that he can take you through more of the details of the actual breaker.
Hello, everyone. Good to be with you guys on this training. So I'm just going to take up from where Rob stopped. So really, I want to go into like the details of the breaker itself. So when you look at the air circuit breakers, the one that we have in the market presently, so you would have the nameplate, which is in the front. So there you have the UL file number and also some details about the breaker, like the frame size, the UL standard, which is the UL 1066, and also the ANSI standards that it's been tested to, and also the UL logo, which is also a CUL, that's also for Canada, which has been tested to the CSA standard as well. So that's what you see when you look at the breaker from the front. Okay. Also, I want to talk about the ratings itself. So we have the rated voltage and we have the nominal voltage. So basically, the rated voltage is it's like the upper limit of reliability for any circuit breaker. So and typically for the breaker to work perfect, very well, the rated voltage will be higher. It will take the upper limit value versus the nominal voltage. So for this breakers that we have, that's the A32 series, we have the voltage is going up to 600 volts nominal, and also We have another series, which is the A40 series, and that one, the voltage goes up to 800 volts. We will see in a little bit what the specific the specifications for these two types of breaker. Also from the breaker nameplate, you will find also the maximum current capacity in amperes, because that's also something that you will find there. The rated short circuit current, you will see that that's measured in kiloamps, and of course that's the maximum fault current that the breaker can safely interrupt at any given voltage. So, and that's an important parameter. It's an important value, because a lot of breakers, since the breaker is primarily meant to protect against short circuit and also overload conditions. So for the short circuit, this rated short circuit current value is very important. So because it defines the maximum fault current that the breaker can safely interrupt without damage to itself or the network that is below it. And in some other, in North America specifically, this is also referred to as the interrupting capacity, and sometimes they write it as KAIC. Also, you will find on the nameplate the short-term withstand current. And Rob did mention earlier on about this, that, when you start talking about coordination, where you have a system that has an air circuit breaker at the main incomer, and you have, sub feeders where you have smaller ratings of breaker, you want to be able to coordinate the protection such that the air circuit breaker, which is at the main panel itself, does not get to respond to every fault that happens, in the system. Because if you do that, then you will have a problem with continuity of service, in the system. Because what this coordination does is that it helps to isolate the fault to the faulty feeder. So and what you do with the current withstand is that you want to introduce a delay in the reaction of that air circuit breaker, so that you allow the breaker that is closest to the fault to be the one to react to that fault. And if that breaker does not, or is not successful in doing that, then the next level breaker will be the one to respond to the fault. This just helps the system to create a system that can isolate fault quickly, and also have that continuity of service, so you don't affect feeders that are healthy. If the main breaker is the one reacting to every fault, it means that the feeders that are healthy will also will lose power at the same time with the feeder that is faulty. So this is measured in number of cycles, and like Rob said earlier, it's 30 cycles, meaning that this from this photo we have here, this is a single cycle. That's the time it takes from the breaker to move from the voltage and the current to move from the positive half cycle through the negative half cycle. That's one complete cycle. So this withstand capability for the air circuit breaker is 30 cycles. So and one cycle is roughly about 16.7 milliseconds. So what we are saying that the breaker is able to withstand that fault in that number of cycles. Now to the specific specifications of the air circuit breakers. So we have on my left here, we have the A32 breaker, power circuit breaker, and then you have the non-automatic switch, which is also known as disconnect switch. So basically, you want the breaker to act like a switch, so it's not offering any protection. If you look at that, both families, we have 3 and 4 poles available. You can have both the fixed and the draw out mounting in both the power circuit breaker and the disconnect switches. The ratings for the A32 goes up to 3,200, both for the fixed and the draw out. And the voltage, the maximum voltage is 635 volt. That's the rated voltage, and the nominal voltage is 600 volt. For this breaker, it can work both in for 50 hertz and 60 hertz frequency of transmission. And like I said earlier on, we have the interrupting capabilities or the capacity. So we have 3 different families here. You have the 65 kA, the 85 kA, and the 100 kA. And if you look to my right here, you can see under the non-automatic switch, we have no IC rating because it's not meant to interrupt the fault. So because it's a non-automatic switch. For the short-term withstand, like I said before, it's 30 cycles at these values. So if you pick the A32R, which is 85 kA, what it means is that this air circuit breaker can withstand 85,000 amps for 30 cycles. So after that, it's not guaranteed what might happen to that circuit breaker. So, and then the operating time is less than 30 milliseconds for the opening operation, meaning that within 2 cycles, the breaker is able to open. And when we say the operating time, we're referring to the time for which the breaker gets the trip command, and then for the contact to physically separate inside the breaker. So that's the operating time, and it's within 2 cycles. And of course, we have the number of operations as well, the mechanical and the electrical. For the A40, the only difference is that we have the A40 going up to 800 volts. And for now, we have only the fixed version for the A40, and the frame size is 4,000 amps. Every other, and of course, at 800 volts, the interrupting capacity is slightly reduced. So it's 65, 75, and 85 as compared to 600 volt, which goes up to 800 which goes up to 800 kA. And it's simple. It's because at 800 volts, you need a more rigid and more robust construction that can interrupt that level of voltage. So that's why the interrupting capacity slightly reduced, because we are now operating at 800 volts. So what it means is this breaker can be used for any of this any of this voltage ratings up to 847 volts. And every other parameter is almost the same with the A32 series. Now to go into like more details about the breaker itself, we have this accessories here. I'm just going to do a quick run through them. We have the accessories compartment, which is one here, and inside there you can have the different kinds of what you call it now, accessories. So we have the shunt trip, the voltage closing release. The shunt trip helps you to give a remote signal to the breaker to sort of open the breaker remotely, while the under voltage is sort of like a protection. When the voltage in the system drops to a particular level, then the under voltage trips the breaker, and it will not allow the breaker to come on even when the under voltage is still present in the system. While the closing release helps you to remotely close the breaker. You give a close command to the breaker. We have the auxiliary contact, the push button locking device, which is in front of the breaker. We also have the cover. The cover is available both in plastic and metal. We have the ready to close contact option, which just it's an indication that the breaker has been charged, whether manually or through the motor operator, and is ready to close. Then the motor operator, like we said, helps you to charge the spring, the stored energy spring of the breaker. More importantly is the trip unit. The trip unit is what serves as, that helps with the protection function that we talked about earlier on. So I'm going to talk about a little bit about that in the subsequent slides. So I'm just going to run through quickly. We have the energy limit maintenance switch, which is number 13 here. And the function of that is during maintenance, you want to be able to put the breaker into an arc reduction mode remotely. You don't want the personnel to go in front of the breaker to do that. So they can remotely put that breaker in that maintenance mode, which is a mode that, reduces the arc flash that can happen in such a situation. We also have the VCM 10, which is a voltage conversion module. And the function of this is only applicable to the A40 series, where you have the voltage going up to 800 volts. So because the trip unit is designed for 600 volts, up to 600 volts to be able to sense the system voltage. So this device helps you to step that down to the values that the trip unit can monitor. And then for the A32, we have the draw out option, and these are the accessories that come with it. The rear terminal connectors are applicable to both the fixed and the draw out. Anyway, we have the safety shutter that protects the personnel once the breaker is withdrawn, so that the life parts of the breaker are not exposed. And if I go into more details on the selection criteria for a product, this is where you can pick a breaker based on the parameters that you want. So you can select either a circuit breaker or a non-automatic switch for whenever you're ready. So we have the interrupting capacity here, number of poles, the mounting type, and then the terminal connection. Do you want the fixed, do you want the horizontal or vertical? And here you have the rated currents that you can select. So what happens is whatever current you select here, we will automatically match the rating plug of the trip unit with that current. But you have the option to select a lower value in situations where, for example, your system is being, considered with future expansion, but right now the facility itself is not using up to that current capacity. So you can use a lower rating plug for your trip unit. And this is an example of the sort of part numbers you can get when you follow this. And this is the same for the A40 as well. So if you follow this selection guide, you arrive at like a part number like this that you can forward to our salesperson, and they can assist you in quoting the price. We also have like a selection guide for the accessories as well, because this is a 1-hour webinar. We're not able to put that in this slides, but we have all the materials after the training, so you can get to see that. But for the trip unit, here's a quick selection guide. Like I said before, the rating plug is matched with the current rating that you selected for the circuit breaker. So if you select the 1600 amps, then we will give you this rating plug. But you may decide that, oh, I want to operate my breaker at a lower capacity and request for an 800 amps rating plug. And for the trip unit, we have 3 types. You have the NM, which is the basic one, the introductory one, and then we have the LCD with ammeter function. And then we have also the LCD with advanced protection. And for all of those trip units, you have 3 types of protection: the LI, the LSI, and the LSIG. I will talk about those shortly. So just to give you like a quick run through the fundamentals of a trip unit. Like Rob said, most certainly every circuit breaker will have an electronic trip unit, but it's important to quickly talk about the thermomagnetic trip, which is something that was used in the past. So looking at that, the operation of that, it uses a bimetallic element, and then a bimetallic element is just 2 metals that has different coefficient of linear expansivity. So what happens is that one of the metal will expand faster than the other one. So when current is passing through the circuit breaker, the temperature will increase. So, and then the bimetal strips start expanding. And so when it expands sufficiently enough, like you see in this diagram here, it's going to trigger the trip bar. And once it does that, then it opens up the contact of the circuit breaker. And that's what happens for the thermal protection. For the magnetic protection, it's just a wire that is wound around some kind of plunger. So when the magnitude of the current reaches a particular threshold, it's going to force the trip bar, to release the trip bar, and then you're going to have the contacts opening up. So that used to be the way, the traditional, or the way that circuit breakers were designed. But then now we have the electronic trip units, which it's like an advanced protection. And one of the things that the electronic trip unit does is that, so instead of having the bimetallic, trip and there's the solenoid, you would have a combination of semiconductor components, the diode, the thyristors, microprocessors. So it gives you more accuracy in terms of the RMS value that you're measuring. Also, there is better temperature stability with trip unit. With the electronic trip unit. So and then the function, the protection settings are adjustable. You have a wider range of adjustment. You can introduce time delay for the long time protection, which is the overload. You can also introduce delay for the short time pickup, and also the instantaneous as well, the instantaneous pickup. So basically, the electronic trip unit is a more advanced, more reliable way of offering protection to a circuit breaker. And typically it's a module that is sort of detachable from the breaker itself in most cases. You also have some manufacturers that have the electronic trip unit sort of embedded into the circuit breaker itself. So just to run a little bit quickly through the types of settings that you have in the electronic trip unit, you can have the long time protection, which is what we call the overload protection, and it has an inverse time function, meaning that the longer, the larger the current, as the current is increasing, you have a shorter response time for the overload protection. So, but if the current increases very quickly, then the reaction time reduces. So you can have both the you can introduce a delay as well for that, and you can have particular settings that you want to put the overload. So it could be at 0.4 all the way to 1 of the rated value that you protection for. Then we have the instantaneous protection. This type of protection, you want the breaker to react immediately to a fault without any delay. So you can set the value at 2 times the current, or 3 times, all the way to 15 times the current. So when I mentioned the ELM, which is the remote maintenance switch, what that switch does is that it's going to operate, it's going to put the breaker in this instantaneous settings, and depending on the setting that you put. So if you put 2 times IN, then that will be the settings for the maintenance switch, meaning that once the breaker can sense twice the value of the current, then it's going to try to trip the breaker instantaneously. Then we have the short setting, which again is useful for coordination studies. Whenever you're doing some kind of coordination study, you want to introduce delay in different feeder circuits or sub feeder circuits. So this is the sort of settings you need for the air circuit breaker. And then we have also the ground fault protection. And for our breaker, we have a neutral current detection sensor, which is an external device. We use the Rogowski coil, and we also have the solid bar as well. So what that does is that is monitoring all the current passing through, is monitoring the current through the neutral leg, and also the 3-phase that is passing through the breaker. And once the sum is not equals to 0, it means that there is a leak somewhere. And so this will trigger a trip for the circuit breaker. And here is just like the way the settings that are available for the ground fault protection. So we have less than 1,200 amps, and we also have above 1,200 amps for the pickup settings. So, and you can also introduce a timer delay as well, just as we've seen in this photo. So just to cap up, that our air circuit breaker, we have them both in 2 series, the A32 and the A40. And we have trip units that are designed to protect the conductors that are downstream of the circuit breakers and the feeder circuits. And of course, we also have accessories that go along with this, and we definitely have the support also to support our customers when it comes to pre-sale, the sales and after sales of all of this circuit breakers that we offer in the market. And with that, I'm just going to hand over to Nate. If we have questions, we will definitely answer those questions right now.